All right, so today we're going to dig into something really cool, a new theory that connects one of the most ancient numbers in all of nature to one of the newest frontiers in technology. We're going to explore how the golden ratio, that golden ratio, might just be the key to finally building a stable, powerful quantum computer.
I mean, let's just dive right in with this question. It sounds a little bit out there, right? But this is the core idea from a theoretical paper we're breaking down today. It's proposing a wild solution to quantum computing's single biggest problem, and it finds the answer not in some sterile lab, but in the patterns of nature itself.
So before we can really appreciate how brilliant the solution is, we've got to understand the problem. And the problem is, well, it's all about how incredibly fragile quantum information is. This right here, this is the goal. It's called quantum coherence. Think of it like a perfectly synchronized orchestra, where all the quantum bits, the qubits, are working together in absolute harmony. This is the magic, you know? It's what unlocks the ability to do calculations that are way, way beyond what any normal computer could even dream of.
But here's the villain of our story, decoherence. The tiniest vibration, a microscopic change in temperature, any little bit of noise from the outside world can come crashing in. The orchestra just falls apart, and that beautiful, complex calculation, it collapses into useless static. Honestly, this is the one problem that has held back quantum computing for decades.
So how in the world do you protect these ridiculously fragile qubits? Well, the paper's solution is so creative. It's not about building a better physical shield. It's about using a mathematical one, a code that's been hidden in the fabric of the universe all along.
And there it is. Yep, that number, phi. You probably know it as the golden ratio. And you have seen this number everywhere, whether you realized it or not. It's in the spiral of a galaxy, the shell of a sea creature, and right in the middle of a sunflower head.
And this isn't just about things looking pretty. Scientists have already spotted phi's unique signature at a really fundamental level in physics. It pops up in these weird materials called quasicrystals. It helps define certain kinds of quantum matter. It's even been seen in experiments with matter waves. It seems like nature has been using this number for a very, very long time.
So why this number? What makes 1.618 so special? Why would it be the superhero for quantum computing? Well, the answer is actually in its unique mathematical personality.
Okay, I know, that quote from the paper looks pretty intense, but the main idea is actually surprisingly simple. The golden ratio is, in a very real sense, the most irrational number that exists. That just means it's incredibly bad at being described by simple fractions. And since a lot of that environmental noise comes in predictable repeating frequencies, which are a lot like simple fractions, phi is uniquely good at avoiding them.
This chart explains the whole idea perfectly. On the left, you've got your standard setup, with qubit frequencies all spaced out evenly. Think of it like keys on a piano, predictable, orderly, and super easy for noise to find and mess with. But on the right, the frequencies are spaced using multiples of phi. This makes them aperiodic. They don't have a simple repeating pattern. It's like trying to find a clear station on an old radio by tuning way, way out into the weird parts of the dial, far away from all the static. You're basically helping the qubits hide from the noise.
And now, we get to the payoff. Because this isn't just some neat idea. This theory makes two very concrete, very testable predictions for how to dramatically improve quantum systems.
The first promise is all about radical efficiency. It's a concept the paper introduces called state densification, and it's a super clever way to reorganize and store quantum information by taking advantage of this new phi-based structure.
Okay, get this. The theory shows that for certain quantum states built this way, you can literally just throw away 25% of the system's components, a whole quarter of the data, and still keep over 99% of the original information's accuracy. It's like a special kind of data compression that's perfectly tuned to the physics of the system itself. Just wild.
Now the second prediction, this one might be even more exciting. This is a direct shot at that big villain, decoherence. It promises a massive increase in how long a quantum state can actually survive before it falls apart.
This chart lays it all out. The standard qubit is our baseline, our 1x. By using this phi-based spacing to protect against all that common low-frequency noise, the theory predicts that a qubit's useful lifetime, its coherence time, could be extended by a factor of phi squared. And as you can see, that's a jump to about 2.6 times longer. In the world of quantum hardware, that isn't just a small step, it's a giant leap.
Now I know what you might be thinking. This all sounds great on paper, but can you actually build it? Is it real? Well, the best part is, yes.
The paper gives a clear, falsifiable plan to test this whole idea, using the exact same technology that quantum labs have right now.
And here is the actual blueprint. It's simple. You create two almost identical 5-qubit chips. On chip A, you tune the qubits to evenly spaced frequencies, just like everybody does now. But on chip B, you tune them using the golden ratio. You can see how the gaps between the frequencies start getting wider and wider? That's Phi doing its thing.
And the experiment itself is just beautiful in its simplicity. You build them, you cool them down to almost absolute zero, you run the exact same standard tests on both chips, and then you measure. Does chip B, the one tuned to nature's favorite number, actually have qubits that survive 2.6 times longer? The prediction is right there, and the result, no matter what it is going to teach us something profound.
So the huge takeaway here is that this ancient, elegant number we see in pine cones and galaxies might just hold the secret to protecting the incredibly fragile heart of a quantum computer. It's such a powerful reminder that sometimes the most advanced solutions aren't the most complicated. They might be hiding in plain sight all along. It really makes you wonder what other secrets from nature are just waiting for us to discover.